Bismillahirrahmanirrahim. Okay, we are studying the Z transform for a few classes, and the last day we have just gone through this time domain, signal, and the representation of ROC for different sort of signals, namely as the causal, anti-causal, two-sided sequence for finite duration signals. And as well as we have also talked about causal, anti-causal, and two-sided sequence for infinite duration signal. And we can found that the difference between the finite duration and the infinite duration signal ROC is as follows. We have the plane like this for finite duration signals. Whenever we move to the infinite duration signals, the ROC looks like circular pattern in different shape. Okay, sometimes it is interior in case of anti-causal signal, exterior in case of causal signal, and of course for two-sided sequences, it looks like angular format. Okay, article number 3.2, the properties of Z transform. You can go to the Procreus book, and then some figure. Okay, so I'll give some example with that figures that is from the book, and this is very important, the properties of the Z transform. Please go through that from the book, and the examples are given for different properties as well. Okay, this is figure number 3.3.5. okay, let me maximize. Yeah, okay, here the pole zero locations and the time domain sequences are presented side by side. We have already found that if our signal is like a to the power n un, or alpha to the power n un, whatever you mention, we have found that the Z transform Z could be looks like Z over Z over alpha minus Z. So the pole location is alpha, so that means Z minus alpha, something like that. Yeah, we have found it exactly. The solution was 1 divided by 1 minus alpha Z to the power minus 1. From there we can find it. So we have done this before. So from there, we have also plotted the poles and the zero locations. If we can remember, the zero location, of course, at the location of 0, and the pole location at the location of alpha, where alpha is it could be, let's say, alpha is equals to 0.5. And how it looks like, this is the pole zero pattern of this kind of signal, where alpha is equals to 0.5. And of course, by this kind of signal analysis, that means alpha to the power n un, if alpha is 0.5, that is whole to the power n, the signal looks like this in the time domain. If the alpha is a negative number, let's say minus 0.5, then whole to the power n. So alpha is minus 0.5. As we already know that the pole location is equals to alpha. So this is that alpha, where alpha is equals to minus 0.5. And for that, the time domain sequence looks like this. We have definitely the stable signal, but we have both positive value and the negative value. Now, if you consider that this pole location is shifted to the unit circle, on the unit circle, so of course the value of alpha is 1. If alpha equals to 1, so 1 to the power n un, so of course we can find 1, 1, 1, and that is nothing but the unit step function. Similarly, if we go to alpha is equals to -1, in that case, the time domain sequences looks like this. You can think in any other ways from one domain to another domain. This is the time domain, and this is the z plane or z domain representation with respect to pole and the zero location. If I have pole and zero, then I can write the xz. Okay, so I can also write the xz equation with respect to poles and the zeros, because the numerator gets the zeros and the denominators gives you the pole values. So you can move from the time domain to the z domain or z domain to time domain. So that actually been shown here in this diagram. So what we can see here, if the pole is inside the unit circle, for the causal signal, you need to represent whether this is a causal or anti-causal signal. First of all, for the causal signal, if the pole is inside the unit circle, then we can say that the system is stable. Whether the pole is positive or negative doesn't matter, but that is inside the unit circle. And we have also learned that what is the ROC for this z-plane representation, as we can know that we need to put a circle that will cover the pole, and the exterior of that is your solution. So that means unit circle is also a solution. That also shows that, okay, the system is stable. And this is also true for alpha is equals to -0.5, the exterior, and that also include the unit circle. Okay. For the second case, where that is on the unit circle, let's say unit circle more than that, of course, that is critically stable. You can say, okay, for the system representation or implementation, we never want this kind of signal, because if it is like this, a bit change of it makes the system unstable. There is a possibility. So we always want this kind of time, the system representation or response of the system, which gives us the stable system. Okay. Okay. If we go a little bit furthermore, try to think about this. If this pole is now shifted out of the unit circle, then what happens? If that is out of the unit circle, that means practically, if that is 1.2, then whole to the power n. So of course, that gives a unstable situation, both for the positive value and for the negative value, let's say -1.2. And we have this kind of time domain sequences. This signal, that means this z domain representation may represent a system, or it can also represent a signal pattern, make a convolutions with the system. So however, we are just talking about if the system represented by the z plane looks like this, the time domain representation looks like this. And very easily, by seeing or observing the z plane representation, we can say that, okay, the system is stable or unstable in the time domain. Okay, so what we have learned here, just changing the value of alpha, you can control your system. If it is an unstable system, you can make the system stable by changing the pole location. Just changing the pole location, not by changing the zero location. So the stability of the system actually depends on the pole location, not to the zero location. Okay, next to the figure number 3.3.6, where we can represent, this is from the book, where we can represent if we have the double poles with a particular point. So how it looks like. No need to memorize the things. This is for the perception. I will not emphasize on the double pole more. However, you can think about this. How we can visualize the double pole. For example, we have alpha to the power n un. For this, where you got the pole, of course, at the location of alpha. Plus, you are taking another signal, which is also alpha to the power n un. So you are adding another signal with alpha to the power n un. So you have definitely another pole where this is alpha. So you can introduce multiple poles of the same system. So of course, in your control system or any other other signal and system courses, you know that how to introduce the poles and the zeros with the system. Okay, whatever the case, if we have a double pole or the multiple pole at the same location, the time sequences looks like this. You can just put the value and you will find first find xz, the magnitude, and then if you can put the value for different n, you'll find that okay, the response is basically stable. At the very beginning, it makes some higher value. It grows to a maximum value, and afterwards it will be decaying. And similar to for negative value, where we have two poles, so it is again gives some higher positive or negative value, and then afterwards it will be decaying. What happens? This is interesting. We have already shown that if you have a single pole on the unit circle, in that case, we got the output like this: 1, 1, 1, 1, and up to infinity. However, if you have multiple pole on the unit circle, it actually gives unstable situation. So your system is unstable both for the negative value and the positive value. This is very interesting. So you can't use the multiple pole on the unit circle. If you use a single pole, it might give a bit stable signal. Otherwise, it will give unstable signal. Now, of course, you understand that if the pole is outside the unit circle, for which kind of signal? For causal signal. We are talking about only the causal signal. For the anti-causal signal, as you can know that the solution, if you have a pole here, the solution is the interior. The solution is interior. So the scenario is completely different. So in practice, most of the cases in our life, we are talking about the causal signal. That means for the right-sided sequences. We very, very rarely talk about the left-sided, that means anti-causal signal. Because in practice, we have all the signals in our hand. So we have the value and we are talking about the past value. So we are taking the present value and the past values to compute the present value and the values we are looking for. So those are the future values with respect to n0. And that is the practical scenario. Why that is a practical scenario? Let's say you want to predict a temperature in future. So what you have, you are getting some data now, and whatever the data you are taking and you are experiencing more and more, by which you can have the future data value. So most of the cases in our practical life, we are dealing with this kind of value, where we have the n, x, n, and the other values in future. You are taking those values and you are getting the final result. Okay, so this is for the, in case of figure number 3.6, we have talked about all are the real poles. Here you have the real poles in the real axis. So that means alpha is a real number. However, the alpha can be a complex value. For example, if alpha is equals to, let's say, A plus minus JB, so we have two poles where this pole is equals to the value of A square, you know, the amplitude A square plus B square root over, and you know the theta value is the omega. So what is the value of omega for a particular omega value? As you know that here, this axis, this rotation is actually gives you the omega value, and this value represent the value of R, R, that is Z, modulus of the Z value. So if we have complex pole here, of course we must have another pole in the other axis. And if they are inside the unit circle for the causal system, then we have the stable situation. Of course, that will give stable situation. And if that is on the unit circle, and we should say that this is not a multiple pole, this is a single pole. This is single pole on the unit circle. Multiple pole means you have two poles at the same location. That is called the multiple poles on the same location. And they have given you critically stable situation. If you have the pole outside the unit circle, of course, it will give unstable situation. This is the last figure at this moment. This is 3.3.8, where it again shows that if you have multiple pole on the unit circle, that this is multiple pole, you have two poles on the same location, and that gives exactly the sharp rising of your signal and make the system unstable. So these figures actually shows us the stability with respect to the pole location for different causal signal. Okay, nice. So we can move to the next section. Okay, we are just covering the different patterns of the Z transform. We have done few examples. We are now confident to plot it in the Z plane, as well as from the Z plane to time domain, we can expect the result, whether this is stable or unstable. Okay, so I have talked about this system before, though we can just give some explanation for a system where you have both left-sided and right-sided sequences. That means you have two-sided sequences. Why this is two-sided sequence? Because you have n is from minus infinity to plus infinity. As we already know that for the Z transform, of course, the magnitude of the Z should be less than infinity. And that is the concept of any sort of mathematical functions. If that is not summable, you can't do the processing, mathematical processing. So we can say in that fashion, the magnitude of the Z is equals to the magnitude of this portion, and you can take the summation out of the modulus value that makes a higher number in that process. So we can write in this way, where if we compare this part to this part, then of course this portion is higher because we are taking both positive and negative number inside. And in a nutshell, we can say that in these sections we have this is a value, and we have this that will also give some magnitude, and this part actually give us the phase. So if we only cover the magnitude portion, we can neglect this, because that carries the magnitude which is 1. So that is inside this value as well. So we need to think that this part should be summable, and that means that should be less than infinity for any sort of sequence. Again, the whole function can be divided in two parts, as we have mentioned earlier, that is from minus infinity to 1 and from 0 to infinity. And if you can look very closely, by definition, the value is, the Z transform is xn r to the power minus n. That is the magnitude. So from a minus infinity to plus infinity, we are just putting like that. And for 0 to infinity, we can write it in this way, xn over r to the power n. So here, whenever we are just changing the notation from minus infinity to minus 1, rather we are putting n is equals to 1 to infinity. In that case, we are replacing n with minus n, and we can find this function. And in the second section, that means in the B sections, we haven't changed anything. We are taking the value n is equals to n. Now we are considering the section A. So now we have two sections, and both of them are infinite series. The left one, that means section A, is a left-sided sequence, or you can say anti-causal sequence. And B is the right-sided sequence, or you can say causal sequence. So now we are considering first the A. From the section A, we can write it very simply that if we consider this, since this is your unknown signal, let's say the unknown signal is unstable. If that is the situation, what should be the value of R? The value of R should be small enough so that the multiplications of these two terms give you a stable situation. So that is the logic. In the section, this is the section where we actually talking about n is equals to minus infinity to minus 1, xn r to the power minus n. And that is converted to n is equals to 1 to infinite and x minus n and r to the power n. Here x minus n, that is a folded version. That is the folded version of your xn. However, if this xn is unstable, what could be the path of the R value? What could be the counterpart of this x minus n? Of course, the R should be small so that it can make the multiplications between these two and gives a stable situation. So what could be the lowest value of R that makes the system stable? Let's say not the lowest value. So what could be the highest value of R? The highest value of R is, let's say, 0.5. That is the highest value. Then what could be the lowest value of R to make the system stable? Of course, 0. And that is why, what is the range ROC of this kind of sequence? What should be the ROC? The ROC of this kind of sequence, let me draw it, is always, let's say this value of R, it's represent 0.5, making a circle, and less than that, all the values of R is the solution for this kind of sequence. So you understand that R should be very small. R should be very small to make the system stable. It might happen that the maximum value of R is equals to 2. Okay, no problem. Then what is the ROC? From 2 to 0, always the lowest value is 0, because you know that all the lowest possible value will, if 2 makes the system stable, definitely lower than that value will make the system more stable. That is very true. And that is the portion we are talking about. N is equals to from minus infinity to minus 1 and xn r to the power minus n. So this would prove that by logic, it will prove that for the left-sided sequences, the solution is always the interior, where you have found the pole is here. Where pole is here, the interior of that is the solution. Okay. So I have actually talked about this with graphical representation, where I have mentioned that the highest value of R, let's say, is equals to R1, and the interior of that is the solution for this kind of sequences. That means for the left-sided sequences. Now, if we consider the right-sided sequences from n equals to 0 to infinite, as we know that the sequence looks like xn and r to the power minus n, or we can write it xn divided by r to the power n. So if this xn is unstable for summation n is equals to 0 to infinity, we need to choose the value of r in such a way so that the total term makes stable. So then what would be the value of r? It should be very higher or lower. It should be lower value. It should be a very lower value or very higher value to make the system stable. Can you answer? What should be the value of r? Higher value or a lower value? Any of you? If xn is a very high value, which makes the system unstable, how you can make the system stable? Definitely by choosing a higher value of r with respect to xn. So let's say that value is equals to R2. For that value, the system makes stable. Now, if you increase the value of R, will that force the system more stable? The answer is yes. If you are choosing, let's say R2 is equals to 0. Let's say not 0. Let's say 2. If R2 is equals to 2, then if I choose more than 2, that means 2.5 or 3, definitely it will force the system more stable and more stable. And that is why we can write it in this way. In case of right-sided sequence, if we have the pole where this is equals to R2 is equals to what? 2. We need to put a circle, and the exterior of that is the ROC, because more than that, all the values more than 2 will be the solution. This is for which case? This is for right-sided sequence. Of course, both of the cases is for infinite series or infinite sequences. So combinedly, what we can say, this is for the right-sided sequences. Combinedly, if for any cases R1 is greater than R2, what is R1? This is for the left-sided sequences. So if R1 is greater than R2, you can take an example. R2 is equals to 0.5 and R1 is equals to 1, let's say 1.5. Then what will happen? We have this R1 and this is R2. Where are those poles? Let's say this is a pole R1 and this is a pole R2. So for R1, this represent for the left-sided sequences, the solution is the interior. Solution is interior. And for R2, this is for right-sided sequences, that is for the exterior. So then we got the common solution like this. But unfortunately, if it is like that, R2 is greater than R1, in that case, you will not get any solution because R2 is higher. This is R2 and this is for R1. So since this is R2 and this is R1. The solution plane R2 is for the right-sided sequences. So that is the exterior is the solution. And for R1, this is a left-sided sequence. So interior is the solution. And you haven't found any common solution between these two sequences. So you don't have any solution for that sort of case. Okay. And that has been given here. So you can go through this. And in this case, the second case, we don't have the ROC and we don't have any Z transform. We have the examples 3.1.3 from the book, Rockies, and 3.1.4. Yeah. This is very important topic for Z transform, where we want to show that not only the mathematical expression is enough for the Z transform, we need the ROC. Why the ROC is important? Let's say there is a beautiful example. Let's say your Xn is this. If you want to do the Z transform, we have done this. We have got the result like this. We are not doing this for this example where Xn is equals to this. I found Xn is equals to this, which is a left-sided sequence. You can understand if I put the value of n, un, how it will be, you will get the value for, let's say for n equals to 0, if you put n equals to 0, you will find, let's say, I'm talking about this sequence. Let me write it here. Let's say xn is equals to minus alpha to the power n, u minus n minus 1. Let's say alpha is equals to, for making it simple, let's say alpha is equals to 1. So then it will be 1 to the power n, it will always give 1. So I'm not writing like this. This is a minus u minus n minus 1. Now, if I put n is equals to 1, then what will happen? I'm trying to write the sequences, draw the sequences. For n is equals to 1, n equals to 0, let's say n is equals to 0, I will find minus u, 0 minus 1. Do you have any value at that location? At n equals to 0, do you get any value? No, because u minus 1, that is 0. So you are getting 0. If you target n is equals to 1, then what will happen? For n is equals to 1, you will find minus u minus 1 minus 1. So that is minus u minus 2 minus u minus 2. So minus 2, u minus 2, is there any value? No, it again got 0. So if you proceed more, you will find always 0 for the positive values. Now, if we target n is equals to minus 1, then it will give a minus u minus 1. So that is minus 1 plus 1 minus 1. So it will give you minus u0. What is u0? That is 1. And since there is a minus, so that means we have some value minus. And this is at the location if n is equals to minus 1. And as you can understand, if we target n is equals to minus 2, you will get this one. So always you are getting something. So what kind of sequence is this? This is the folded version. Definitely you can understand if I neglect this, this is a shifting. So this is the folded version of un. So it is a folded version and shifted one sample to the right. Okay. So it shows that if it is your xn, if you do the Fourier transform, sorry, Z transform, you will also get the same mathematical expression. So for the both sequence, if you go for the Z transform, you get the same mathematical expression. That definitely makes our life difficult without ROC. Why? If you want to do the inverse Z transform, there could be two solutions. As I have already mentioned in the previous lectures, in the Z transform, that is a one-to-one function, but this is a one-to-many function. So that means if this is in the Z domain, if you want to do the inverse Z transform, then you may have two solutions. One is alpha to the power n un, and another one is minus alpha to the power n u minus n minus 1. So in which direction you should go? How you can find that? Okay, then you need what? The ROC. How? For example, if this is the case, you are from the time domain to the Z domain. What is the ROC for this case number 1? What is the ROC? The ROC looks like this. Let's say this is a pole alpha, this is a circle, and the exterior, because this is a right-sided sequence, we got the exterior. So this is my ROC. So if I have this ROC and this expression, mathematical expression, with the combination of these two, I can say that the result will show in a very short time how to do the inverse Fourier transform. So we can say that, okay, this is the solution, because this is a right-sided sequence. We have two possibilities. One is here, and this is the second possibilities. So by seeing the ROC, we can say that, okay, it must be a right-sided sequence, and this is my final result. On the other case, if I have the ROC looks like this, let's say this is alpha at the same location, and the ROC is interior. This shows that, of course, the time domain sequence is the anti-causal sequence. So then we may have two solutions, but I will stick to this solution because my ROC is like this. That shows that that is the left-sided sequence. So the motivation of this example is that to show only the mathematical expression is not enough. We need both the ROC and the mathematical expression to get back to your original time domain sequence. And that is true for all the Z transform. So I have written those things here, so you can go through this and you will find it very simple. The example is given, so please go through all the examples in the book. They are very helpful. Okay. By the help of constant coefficient difference equation, we can write, this is the general equation of the constant coefficient difference equation, yn minus, this is from k is equals to 1 to n, ak, they are the coefficient of the feedbacks, these are the feedbacks, yn minus 1, minus 2, minus 3, plus the inputs, the current input k is equals to 0, xm, and k is equals to 1, those are the past input values. N minus 1, n minus 2, n minus 3, you already have those values in your hand. So if you have the feedback and you have the present and the past inputs, this shows in general the difference equation for any purpose. And if we do the Z transform of these sequences, then we can find yn can be written as this, and definitely the summation and the constant coefficients, they will remain the same. and the yz and z to the power minus k, where the delay value is a function of k. Similarly, plus summation bk, the coefficient remains the same, xz z to the power minus k, where k shows the delayed values of the n input n. Now from this equation, if we extend this one a little bit, we have found this. That means y divided by x, which is our response of the system, is equals to this, where this shows the zero locations and this shows the pole location. We have already mentioned this kind of equation where the numerator actually came from, if I go a little bit up, you will find that the numerators actually came from this x component. So that means it depends on your inputs, your input values, and those coefficients of your input with the for different samples. And the denominators actually represent the feedback of your output. You have the output. So in a system, if you have the output and you have the delayed version of that, if you need that for any sort of response, this is your xn input, and this is the delayed values of the y. So we can write this is actually y n minus 1. It might happen that you need another delayed, so double delay of your output, and that can be written like this. Let's say here is the plus, so it actually looks like this, and this is y n minus 2 according to the structure. We'll talk about this. We have already talked about this structure. Then this equation. Similarly, you may need the input y n minus 1. So you have the y n is the current input, and you need y n minus 1, the delayed version of that value. You need to delay it for the future one. So the previous input, you can say the previous input, because xn minus 1, xn minus 2, if n is equals to 0, that means the current value 0, then it shows n minus 1, just the previous value delayed, and this is n x minus 2, that means the 2 delayed value. So if I have xn, put a delay z to the power minus 1, it actually gives xn minus 1, as we have shown for the y output as well. So try to think about this always. The zeros actually depends on your delayed values of the input, and the poles always represent the delayed values of the output. So if you want to design your filter, mostly we introduce the poles by giving the feedback, and no pole system is known as the FIR system. We'll talk about this. That means where you do not have any pole, you only have the zeros. You can design your filter with only zeros or only poles, but definitely they have their own advantage and disadvantage. So we'll discuss on those things in detail in the next semester when we have talked about the filter design. Now we can move to the inverse of the Z transform. There are different ways how you can do the inverse Z transform. One of the methods is the expansion into a series of terms in the variables Z or Z minus 1. This is number one. Number two is the partial fraction expansion and a table lookup. So to see the table, we can find it. And there are some other methods as well. So we actually gone through these two different methods in subsequent section. So the inverse Z transform by power series expansion, very simple. We have the example 3.4.2. I have just gone through this example 3.4.2. This is from the book. Let's say xz is given here. So we are now at the z plane or in the z domain, and it is given like this. Of course, from this equation, you can also find the pole and zero location, and you can draw the ROC. But since you are in the z domain, we need to express what is the ROC. So that means this is the mathematical expression. What is the other information you need to go back to the time domain? Of course, the ROC. For A, it's given that the ROC is more than 1. And in the B, it's given that ROC is less than 0.5. So if I ask you one question, if we want to do the A, how the time domain sequence looks like? Will that be a right-sided sequence or left-sided sequence? Any of you can answer this? If we think about the ROC is more than 1, what kind of sequence we are targeting? Left-sided sequence or right-sided sequence? The answer. None of you can answer this. The ROC is interior or exterior? By representing this ROC, Z is greater than 1. Yes, 72.
So right-sided sequence?
Yes, thank you. That means this is exterior, this is 1, and more than that. So what kind of sequence is this? Definitely this is a causal sequence. That means right-sided sequence. So in case of A, we are targeting right-sided sequence. If you target the right-sided sequences, how it looks like at n equals to 0, n equals to 1, 2, 3, you have the samples. If you have the samples, then what should be the power of the Z? The power of the Z, according to the Z transform, you have your xn and z to the power minus n. So put the value of n there. What would be the first power of z? Z to the power, definitely 0. And then second power, z to the power minus 1, z to the power minus 2, z to the power minus 3. So that sort of power of the z we are looking for, because we want to move to the time domain. So if we can find this kind of power, so this expression can be expressed with a power combination of z to the power 0, z to the power minus 1, z to the power minus 2, z to the power minus 3, where maybe there are some constant coefficient a0, a1, a2, a3, where we can write the xn is equals to what? Xn is equals to a0, a1, a2, and so on, where a0 is the 0th location. This is at the location n equals to 1 and n equals to 2. This is the philosophy. So we need to express this equation for A in such a way that we have the coefficient, then z to the power 0. We have the coefficient z to the power minus 1. We have the coefficient z to the power minus 2. Otherwise, there is no other way, because we know that that is a right-sided sequence. Right-sided sequence means n should be 0, 1, 2, and so on. I believe that is clear. So if we can move on, I have already written those things here. This is the example we have started. So what was our example? The example was given xz is equals to 1 divided by 1 minus 1.5 z to the power minus 1 plus 0.5 z to the power minus 2. That was the value. So we can write in this way. We can divide. Exactly, we are dividing. But our target is to make the power. What should be the power of this? That should be a z to the power minus value. Okay. So just doing this expression, I'm not explaining these things because you can do it better than me. And after doing this, we have found this kind of expression. This expression should be looks like this: 1 plus 3 by 2 or 1.5 z to the power minus 1 plus 7 by 4 z to the power minus 2 plus it will goes on. Okay, you do not need to do you can do it up to 3 terms or maximum 4 terms, not more than that. That is enough. So if this is the value, what is this? This is actually your xz. This is your xz. If this is xz, now you can say that this value actually represents the n is equals to 0. This value represents n is equals to 1, and this value represents n equals to 2. So in that way, we can find what is the value of xn, and this is the time domain expression. So we have started with this, and we have converted to the xn time domain sequences, and that's it. Okay. If we look back to the B, what happens? This ROC, it shows that less than 0.5. So of course, this is the interior. That is this is an anti-causal sequence. So if you want to express anti-causal sequence, the power should be positive, because in that case n should be a negative number. So if I target the value n is equals to -1 location, that should be z to the power minus n. It mentioned that z to the power minus -1. So that is z to the power +1. But for -2 location, it would be z to the power minus -2. That means z to the power 2 value. So the power of the z should be positive. From there, you can find the location. What is the tricks? If you can compare with the previous example, with this example, we have written like this. In the second case, we will swap it in a way that the highest power, negative power, should come first, then the second one, and then third. So that is 0.5 z to the power -2 minus 1.5 z to the power -1 plus 1, and then divided to 1 value, divided by 1. So that's what we have done here. Half z to the power -2 minus 1.5 z to the power -1 plus 1, and then divided by 1. And if you can go through, you will find this expression. What does it mean? What is the power of z to the power 2? So that is at the location of -2. N is equals to n at the location of -2. You are getting the value is coefficient 2. N at the location -3. You are getting the coefficient 6. N at the location -4. You are getting the value 14. What about n -1? -1. What should be the coefficient value? Can you answer? For n is equals to -1, the coefficient value, yes, 48.
Sir,
48. I can.
sir, z to the power 0, z square.
I'm talking about what is the coefficient for n is equals to -1. That means z to the power 1. What is the coefficient from this equation?
Sir, 6, sir.
That should be 0, because you don't have that kind of sequence here. That's why the coefficient shows that is 0. Okay, you understand. And what is the coefficient of for n is equals to 0? Again, there is no term, constant term here. If you have any constant term, that means let's say 5 or 6 without any z, then you can find that what is the coefficients. Again, since there is no such kind of term, we can say that the coefficient is 0 again, and we have found like this. So this is for n equals to 0, this is for n is equals to -1, this is -2, -3, -4, and -5, and so on. You can write it like this. Okay, so that is the inverse Z transform by the expansion method, series expansion method. In the next day, inshallah, we'll talk about how we can do it by the partial fraction expansion, where we can also get some extra advantage for different purposes. Okay, so okay, I believe that is enough for today. If you have any question or comments on today's lecture. Do you have any question or comments we can discuss on the Z transform? Okay, so it finds that everything is good.
Sir, one
Yes.
second, sir. My attendance, sir. I was there from the beginning, but I went to the washroom. Sorry, sir.
Okay, thank you very much. First of all, I'll end the class, then we'll talk about the attendance if necessary. Okay, thank you for your participation.